Calculus 30, this is the start of chapter 11. We're talking about integrals. Now, we've talked in chapter 9 about antiderivatives, and all the chapters before that were about derivatives and differentiation and what they mean, right? Derivatives are often interpreted as instantaneous rates of change, right? So integrals is sort of what happens when we go backwards. Instead of differentiating, we're going to integrate to go backwards. So if we are given an expression for a rate of change, we can actually determine what the actual position function is if we integrate. So it's the opposite sort of operation, really, of differentiating, okay? Derivative and then integral. So there's some notation we need to talk about and that sort of thing. So this lesson is going to cover, in your Red Stewart textbook there, it's going to cover 11.1 and 11.2. And so we're going to get started on this today. So as you know, there are two main branches of calculus, which we've talked about before, and I just mentioned them: differential calculus and integral calculus. So we've talked about both of those. We're just getting into the integral calculus. The main concept in integral calculus is the definite integral. Okay. Now, a definite integral is where we find an actual value for things like area under a curve. In chapter 10, we just talked about the using the antiderivatives and the integral to find the area underneath a curve, or a curved line or a straight line, and above the x-axis. Remember that? We also just got finished talking about, in 10.2, about finding the area in between two curves. So if we have two curves like this, from A to B, we can find the area that's encapsulated between those two curves. So the integral is often interpreted as an area, okay, as an area. So the definite integral is an actual value for the integral, or a value for the area. The indefinite, so where is indefinite? Definite solution to an area problem. Okay, definite. I'm trying to find indefinite integral here. Okay, so, well, I guess, I don't know where I can see it. I can't see it now. Anyways, the indefinite integral, which I'm sure will come up a little bit later here, indefinite integral, is the expression. The expression. And that's where you need to add your plus c, right? It's the expression for the area. If you don't know where the bounds are, or if you haven't determined where those bounds are, there's an expression for the area. You just have to kind of plug in those bounds. So there's definite and indefinite. So let's take a look at this over here. Okay, so over here we have notation for an integral. I don't know if you've ever wondered, or you've seen this in various calculus textbooks. This symbol right here, it kind of looks like an F without a little line in the middle, but it's actually an elongated S, okay? And it kind of, it's an elongated S, and it kind of represents, summa, or sums, okay? Because in the integral, you'll see that, and we're going to study this a little bit more, a little bit later as we study Riemann sums, okay? And that's kind of in the next part of this, of the next course, really. So we're not going to talk about a lot now, but Riemann sums would be like adding up, and we've done this already a little bit, adding up rectangles or trapezoids that would roughly approximate, right, the area of the that's underneath the graph or the curve. So we've done this already. Equal, kind of, that's not equal, but equal with rectangles, for example, and the more rectangles we have, right, the tighter, the closer they are, the narrower they are, the closer they can get at the top, and the fewer gaps that we'll have, right? And so if we add up all the areas of an infinite number of rectangles that would fit underneath the curve, that would approximate the entire area. So what I'm saying is that if we had the same curve, okay, and instead of rectangles this wide, we had rectangles that were this wide, okay, can you see what I'm trying to do there? Like they're super narrow, there wouldn't be as many gaps underneath the function, or there wouldn't be as many overlaps on top of the function. So it's a sum. The integral is really a sum, and that's where it's based out of, the definite integral. But we don't have to do rectangles, okay, because we can use this concept of the integral and anti-differentiation. We can use that concept to be extremely accurate and to have no overlap and no gaps. We don't have to add certain things. But that's where this elongated S comes from, okay, the sum. So down here, let's focus on this. Again, this is from your Red Stewart calculus textbook. This is also called an integral sign, so that's just an integral sign. It's an elongated S, It's an integral, it's a limit of sums. So it's what the sum would be of an infinite number of rectangles that would fit underneath a curve. All right, the f of x part, so the function that's underneath here is called the integrand. Okay, that's the integrand. The a and the b, as we've seen before, like this, a and b, they are the limits of integration. So we call those, the limits of integration. And that's the a and b here. The lower limit would be down in the bottom, and the upper limit would be up here. So we would start at the lower limit and end at the upper. Okay, so what's also important is that you should interpret this as really a single symbol. More importantly, I would like you to consider, and I have this outlined in red already, the integral sign and the dx. We always have dx. Now, why do we do that? Because what we're talking about here is we want to take the integral of this function with respect to x. The dx kind of means with respect to x. Or really it's now think of it this way, okay? Those little rectangles that I explained that were underneath here, okay? Think of it this way. We find the area by adding this f of x is the height of each rectangle, and this dx is like the small difference in the x values. We bump the x over a little bit, and that's the width. So it's kind of like height, width, and we add up all of those rectangles that would fit under there. But we cannot, and this is the important part of this point here, we cannot separate the integral sign with the function with the d of x, or dx. They are not three separate things. They're really only two things. The integral is the integral sign and the d of x. They always have to go together. So we're taking the integral with respect to x. Think of it that way. And the integral of what? Of the integrand. That's the function in the middle. Okay? So we always have to have integral and then dx on the end. Okay? Don't forget either one. Okay, so the process of calculating an integral is called integration, as I've already mentioned here in the preamble. Okay, there's a few things I want to remind you about. Now, this is in your textbook, and we're not going to do this from scratch for the sake of time, and I don't want you to get lost in some of these calculations because you actually have done this stuff before. I just want to walk you through it. So for those of you that don't like copying out the examples, you'll be happy with this one because I'm just going to point out what I've already done. You do not have to write this out yet. Excuse me. So what does this say? For the special case where the function is always greater than 0 or always positive. So that would be a function like this where we have a function always above the x-axis. In that case, the integral of f of x with respect to x is equal to the area under the graph and above the x-axis from wherever a is to wherever b is. Now that seems pretty straightforward. The tricky part is what happens if this is not the case. So that's what this next example, that's what this one is showing us. So here I have a part of a function of y equals 3x squared minus x, 3x minus x squared. That's this right here. And it's supposed to be a parabola. That does not bend back up. It's just a bad drawing. But there's part of it that is above the x-axis, and part of it is below the x-axis. So if we used the idea of finding the integral from a to b, what we have to understand is if we did this separately, this would turn out the a1, and I did this over here. This is a1 right here. Okay, a1. I found the antiderivative of this function, which is right here. See that? Okay. And I evaluated it from 3, this is 3, as an upper limit, and 0 as a lower limit. So capital F of 3 minus capital F of 0. That's how you find the area underneath this graph and above the x-axis from 0 to 3. Okay? So that should be, you remember this? Do you remember doing this? You've done this in chapter 10, just a few days ago. So capital F of 3, we have put 3 in there and evaluate it. capital F of 0, put 0 in there, evaluate it, comes out to this right here, which is 9 over 2 units squared. It's a positive value because it's above the x-axis. Now, if we did A2 separately, and I've done that below, A2 separately would be the integral from 3 to 5, you see? And so it's the same function, so we use the same integral, but I'm going to go f of 5 minus f of 3. And you'll notice that you should get a negative value. So remember we learned last chapter that technically the area that is between the curve and the x-axis, if the x-axis is above the function, that area comes out negative. Okay? So you should remember that. Just mathematically, that's what happens. So this would be positive, this would be negative. The total combined area of A1 plus A2, okay, if we were to add up the actual values, it would be 9 over 2 plus negative 26 over 3. And we'd actually come up with a negative value. And that's because this area A2 is a little bit larger than area A1. It may not be reflected accurately in my diagram, but it's actually a little bit bigger. So that's why we get a negative area. And you're thinking, okay, what is the big deal here? Well, the point is this. It doesn't matter if the graph goes above the x-axis and then dips down below and goes above again. The beauty of this fundamental, they call this the fundamental theorem of calculus, is that because of the nature of the function, it basically, all this is taken into account, okay? As long as you have the upper limit as the far right, that's B, and the lower limit as the far left limit, that's A. And watch this, I did this just not by splitting it up into two pieces. And look at this, we got the exact same answer. So if I used this function right here, and I took the integral from 0 to 5, that is, what is my combined area underneath the graph between 0 and 5, it automatically calculates this as being negative and this as being positive. Okay? So it'll give you an area. Now, that's great because you don't have to split this up and just mess around with the little pieces. But if you are now talking about an absolute value of area between the curve and the x-axis, you would still have to split it up, if you know what I mean, right? Because it's actually going to take this area away from this area. So, what's the bottom line? If you want to know the area between the curve and the x-axis only, it's going to be a positive area above the x-axis, and it's going to be negative below, so you have to keep that, reminding yourself about that. But because functions, because we're often very interested in this value, not as an absolute value, but as a combined positive, negative value. So think about this as, well, you guys maybe aren't there yet, but think about this as population growth. This would represent an increase in population. This would represent a decrease in population. So this integral would represent the net increase or decrease of a population, let's say. Okay, so you have a rate of change of this, and so if you integrate, you're finding the sort of the net overall, population, whatever. So it increases a bunch here, but it decreases a little bit more over here. So the overall net change would be negative, and that's we're very interested in that in many aspects of math and science and sociology and biology and all that sort of stuff. Okay. So, fundamental theorem of calculus uses antiderivatives, the concept of integrals, to calculate area under a curve. All right. So as we move forward here, let's differentiate between definite and indefinite. So as I mentioned before, definite integral here is a number, right? It actually could represent an area. It could represent a displacement. If we're talking about a speed over time, if that's the graph, then it could represent displacement or something. But it's an actual number. And there would be limits of integration that would be attached to the integral sign, okay? So clearly this table above that I'm showing you right here, this one that I'm circling, that is a table of indefinite integrals. There are no limits of integration, and basically it's the same as antiderivatives. So a definite integral would have limits of integration, and it would be actual number value that you would get. The indefinite integral, as I mentioned before, is an expression. There are no limits of integration attached to the integral sign. And you do have to remember plus c. Okay, plus c. So this is a table of indefinite integrals. I believe this is in your textbook that you have in front of you. You would be well to memorize many of these, but you will have this as reference as you move through. So I wouldn't expect you to memorize all this right now. Okay? So as you look at an integral now, you'll be able to tell whether it's a definite integral or an indefinite integral. And this example right here, number 1, and I actually think I am going to do this with you. I kind of meant to erase this. So let's do this together from scratch. Okay? Are these definite or indefinite? Well, I guess they're mentioned definite. But you can see that they're definite because of the limits of integration. See that? Everything else is the same. If those limits weren't there, then they would be looking for an indefinite integral, which is an expression for the integral plus c. Okay? It's an expression. That's a function, really, another function, plus c. Okay, so let's evaluate this one. Now, this is kind of interesting stuff here. Maybe I'll use yellow because I think, oh boy. Yeah, you guys want to grab those lights? I didn't realize the red is pretty terrible for you. It looks really good on my screen right here, but if you want to hit those lights, I'll use yellow from now on because I know that really jumps out. Or pink? I don't think I have pink. I have this blue is pretty cool. This blue, how's that?
Oh, yeah.
That's awesome. Okay, you want that or the yellow? What do you want? Blue. Okay, let's do blue. Now, before we get into antiderivatives and all that, let's think about this for a second. Okay? The function is 2. The integrand is 2. That's y equals 2. Now, I think I have something down here. Oh, come on. Where'd it go? Oh, what? Wow, I copied that twice. Isn't that great? So, look at this. Y equals 2 would be this line. I'm going to show it right here. I don't know what color that's going to be. Oh, black. That really helps us out, doesn't it? Okay. It's going to be this line right here. Pen properties. Change that to, you guys like the blue.
Yes.
How about that? Okay.
Yes.
So. Okay. But you see how this is y equals 2. So, if we're talking about an area under the curve is y equals 2. It's a straight horizontal line. And the limits of integration would be from -6, so here is my a value, all the way to 7. Here is my b value, 7, right there, b. You see that? Now this is an easy one to envision how this integral can be interpreted as an area. So what this should be is it should be 1 unit high, 2 units high, that's 2 units high by what? 1, 2, 3, 4, 5, 6 times 2 is 12, 13. These are by 2. Woohoo. 13, right? Is that correct?
Yeah.
So 2 times 13, this area is what? 26. Okay, the area is 26. Now what we're going to do is we're going to integrate this, evaluate this definite integral, and we're going to see if this matches up. Okay. So I'm going to change the yellow here so we have a difference. But okay, so what's going to happen here is that I'm going to find the antiderivative of this right here, aren't I? So what's the antiderivative of 2?
2x.
Very good, 2x. And I'm going to evaluate this from -6 to 7. Now, have I ever showed you this notation yet with a kind of a big straight line, lower limit, upper limit? Okay. Well, beware. You're going to see this now. And what this means is we're going to evaluate this function evaluated at 7. And we're going to subtract the function evaluated at -6. So this is going to be 2 times 7 minus 2 times -6. That's going to be 14 minus a -12, or 14 plus 12. 26. Unit squared. Definite integral. Try and include your unit squared, please. Wow, excuse me. Still not over this cold here. So that's a pretty simple example. We can easily draw that and see that the area does correspond to this definite integral. You good with that? Okay? All right. Here are some more that are maybe a little bit tricky. And like I say, this is a bit of a mess here right now, but this is B, okay? This is B. Let me walk you through B, and instead of us doing it, we'll do some more later. But again, I want to get through this lesson for you in a timely fashion that I think you can handle. So I don't know if we need to do all these questions from scratch together. So I'm going to point out what I've done. B, right here. Okay, that is a definite integral because it's got the limits of integration. You see that? So I'm actually looking for an area underneath this curve, or in air quotes, underneath the curve, right? Combined with positive that would be above and negative that would be below. I'm looking for the overall net area between the curve and the x-axis. Okay, can be positive, can be negative. And so how I do that is I take the antiderivative of this integrand. So how do I do that? Well, this is a x to the 1, so I'm going to make that x to the 2. Then I'm going to divide the coefficient by 2. I'm going to keep that negative sign. This 7 becomes a 7x. So do you see how we have, over here, it's 6 over 2, x squared minus 7x, and that's a 3. So 6 over 2 would be 3. You can simplify that. So if it's going from 5 to negative 1, I'm going to evaluate this antiderivative at 5, right there. And I'm going to evaluate the antiderivative at negative 1, which is going to be that. Now I do have this diagram over here, and I'll get to that in a second. But if we evaluate f of 5 minus f of 1, I have 40 minus 10 is 30. So that should be the overall area underneath this curve, or the positive area above minus the area below, or added to the negative area below. And I know this is a bit of a mess here, but I've done this already before, so I just want to show you what I did. What I did is I counted, literally tried to count all of the squares, all of the square units, the 1 by 1 square units, added them all up and approximated, and above here I've got about approximately 44 units here. And underneath I have approximately 14 units. Okay? So 44 plus a negative 14 gives us a 30. So all in all, what I'm trying to say is that the graph corresponds with the math, or the calculus that we're doing on the other side. All right? Any questions?
So we have gotten 0 as the area value, or 0 units squared if it was from 5 to negative 5, right?
If it was from 5 to negative 5, you may end up with a 0
Right, so
square. Yeah, well, this is 1, 2, 3, 4 this way. So if you had 1, 2, 3, 4 this way, it'd be negative 3. Then yeah, you could have the integral value could be 0. Yeah, remember it's like a net value, right? Think of this as people coming to your business, becoming new clients, and then down here, this is people leaving your business, like taking their business away. So if you had 44 people come, new clients, but you had 44 people leave, your net. Right? Okay? So you have a rate of loss and a rate of gain. And if those totally balance out over the same amount of time, it would be 0. So yeah, it totally could be 0. No problem. Could be positive. And that's why area under the curve now is a bit misleading, because I've told you for years, since you were little bitty babies, that you can't have a negative area, right? So this is where you have to understand that the parallel there fails a little bit, because it's not only the area under the curve. If the function is exclusively above the x-axis, then yes, the integral equals the area under the curve. But if that graph dips below the x-axis, then it's not exactly equal to the area under the curve and between the x-axis there. Okay? Get it? So that's why integral is area? Yeah, kind of, for the most part. That's helpful, I think, to think of it that way, but not always the same. Okay, now, so let me just back up here for a second. I just want to take a look at something. All right, so you need to talk about the properties of integrals now. So this is in your textbook, Red Stewart, page 503, if you want to go there. And what you'll notice is that there are properties of integrals that are much the same as properties of derivatives. So these are going to look exactly the same, just with the new notation. So if we take a closer look here, this c is a constant. So if you have a constant times a function of x, you can actually bring that constant out, because remember, when we were to differentiate, right? The constant would just kind of hang around there anyways. Like we would multiply the exponent by it, whatever. Like it was not really part of it. It just multiplied by whatever the derivative was. So for an integral, you can actually bring a constant out in front, and it won't affect the end value. So that's the constant rule. Okay. Another property is if you have two separate functions and they are added together, you can treat them as a sum, as one function, or you can split them up. And really, that's what we're doing for all of these ones that we did up here before. So you see this right here? That's like function 1, subtract function 2. And that's really what we do anyways. You don't even think about it. So we evaluate them separately. Okay? That's all it's saying. So that's not really very earth-shaking. The same is true for definite integrals. Notice these are definite integrals. And the integrals, the limits of integration still hold true if you separate them, which is exactly, again, really what we did here. The limits of integration here from, well, maybe where's that one that new notation? Ah, where'd it go? I missed it. Where's that new notation? In yellow. Oh yeah, right here. So this is just one, but if we had a polynomial, each one would have the same limit of integration. We could split it up that way. So I'd encourage you guys to work on the problem plus questions as well. In your textbook, here's the problem plus question. If you want a challenge, go ahead and do that one as well.